Okay. All right. So welcome, everyone. This is our second to last colloquium for this semester. So today it's my pleasure to welcome Jorge Noronha from UIUC. So he is a high-energy theorist with a long history working on relativistic hydrodynamics, neutron stars, and I guess we met at KITP this year and had a lot of fun. Thank you for inviting me to your program.
Thank you for inviting me here.
Yes. So anyway, he did his PhD in Frankfurt, was a postdoc at Columbia, and then was at the University of Sao Paulo in Brazil for 8 years before moving to UIUC just before COVID.
Yes.
Probably started at the same time as me, actually. Hopefully we'll have a great colloquium. I think he's a very good speaker, so yeah.
Okay. Thank you so much, Andy, and thanks a lot for the invitation. And I had a great day so far. Talked to a bunch of people. Had some very nice, interesting discussions. Oh, so you're switching off something here? Okay, very good. So let's see if this works. It does. Okay, so thank you very much for the invitation. I'm very happy to be here in Boulder. And so what I'm going to tell you today is about relativistic fluids and how these ideas in really like the whole framework of hydrodynamics, how that is actually very useful for understanding different systems, very tiny systems, like systems that appear in particle physics and in high energy nuclear physics, the collision of nuclei, and going all the way to neutron star mergers. So the first thing that, of course, you all know is that fluid behavior appears everywhere. When I mean everywhere, it's really everywhere in the universe. So if you go to fantastically large cosmological scales, like here for the simulation of dark matter, at very large structures in the universe, so you have, people do things that, this already looks kind of like some fluid calculations. Then if you go many orders of magnitude lower, so here, this is the image of the black hole in the center of our galaxy, this Sag A star. So fluid dynamics is fundamental for creating these pictures. Then you go to neutron star mergers. So this here, two very, very dense objects with a radius of around 10 kilometers, they collide, they produce these gravitational waves and a lot of interesting electromagnetic signatures. And fluid dynamics is very important. Then, of course, the human scale, as we all experience. So fluid dynamics is really everywhere. But if you start thinking about it, why are fluids so ubiquitous in nature? So this is a sentence that I really like a lot. It's one way to understand is that nature can produce complex structures even in very simple situations, and can obey simple laws even in complex situations. So this, I think, the emergence of fluid dynamics everywhere in nature is a sort of manifestation of this type of phrase. But why? Okay, so let's go more technical. Why do we see fluid dynamics everywhere? Well, first, because in general, this is really based on very general conservation laws. So for example, you have energy conservation, as you can see from this nice example, momentum conservation, and if you think about it, you're teaching your fluid dynamics course, non-relativistically, you think about energy conservation, momentum conservation, and also mass conservation. This means that whatever came out and crossed this surface will cross this other surface later, because mass is not really created or destroyed in this case here. So, and another important part that is probably not as emphasized as it should be is the presence of a very large separation of scales. And what I mean very broadly is the following, that normally you see fluid dynamics occurring when you have some very tiny little scales, for example, associated with the mean free path of molecules here in the air, right? So these are these little things colliding here. And then this is very different from the typical scales that you see with a variation of conserved quantities, for example, densities or energy and momentum, which here in this case would be sort of like in the centimeter scale. So you see some simulation of a fluid passing through this car. So broadly, if you divide the little by the large, if this number turns out to be very, very tiny, normally this is a situation where fluid dynamics occurs, okay? So this is a sort of like a nice way to talk about it. When the Knudsen number, as it's written here, is small, normally you expect fluid dynamics to occur. And that's what I mean. The fluid dynamics is a great approximation in this case. So how do you describe this? So once you put it together, right? So for example, in the classical sense, you can just use Newton's laws, and you have just basically F equals ma, that's what it is. Ma here, and then this is the force. So you have the mass and the acceleration here. This gets a little bit more complicated. This v here is the velocity of the fluid at every point in time and space. This is the density of the fluid, and here you have the different forces. So here just the gradient of the pressure, here some gravitational force, and this is an important part for this colloquium, which is basically the following. So here, if you stop here, no entropy is produced. Okay, so that's what we'll call a standard perfect fluid. But here, that's the part where viscosity appears. So viscosity appears in this little coefficient here. And here is where we start thinking about the separation of scales. If the Knudsen number was truly zero, you could just end up with something like this. But once you have corrections, you have these viscous corrections, what you do, you start writing down contributions that can enter and create these forces that change and create acceleration for your fluid. And these equations are the standard Navier-Stokes equation that describe the flow, in this case here, of an incompressible fluid. And of course, I mean, these equations look simple, right? Just some equation. There's just some nonlinearity appearing in the interaction of velocity, but it turns out to be a notoriously hard problem in 3 spatial dimensions. And this is Gabriel Stokes. This is a little photo of him here. And to the point that this is so hard that it can actually make $1 million if you understand some properties of it. And this is probably the hardest way to make $1 million in your life. And that's related to this Millennium Prize problem. It's a very solid problem in mathematics. It basically tells you the following. Imagine that you get these equations. See what happens at very large times. Can you show that well-defined initial conditions will either diverge or become weird at late times, or can you show that they're fine for all times? Whoever can actually prove this to the standards of a mathematician will make $1 million, and this problem is unsolved. So, but of course, extreme fluids in the sense that I'm going to consider in this talk are those where this Knudsen number, this separation of scales, is not very well defined. So for example, you can have extreme fluids without going to crazy systems. For example, when you have rarefied gases in high altitude flights, actually engineers have to worry about this, so you can get Knudsen numbers there of order 1. And also, this is a kind of cool thing. It's called a microfluid device. So this is, this is red blood cells, and the thing is basically there's no real separation of scales between the size of this thing and actually the size of the little blood cells. Okay, so people have been thinking about this for a while. But what are the kind of systems that I'm going to consider here? The frontier of fluid dynamics that I'm interested in has to do with this type of systems. It's when, one way that you can create something really crazy is when the big scale, you can shrink it so much that it's not even the size of an atom, but it's actually even smaller than that, the size of a nucleus. So imagine that you can redefine the big macro scale going beyond the atom to the size of the nucleus, or even the size of a proton itself, okay? So the question is, of course, here, for those that don't work in high energy, those are my units, which are natural only for people that work in high energy. But then the point is that, if this is even your big scale, how do you treat this system? Can such a thing, even the proton itself with all its quarks and gluons inside, can this behave like a fluid? Another frontier, which has to do not with the very, very tiny, but with the very, very large, has to do with fluid dynamics under strong fields. And by strong fields, I mean strong gravitational fields, for example, like in neutron-star mergers, and also very strong gravitational fields and electromagnetic fields. That is, that happens, for example, for the plasmas that surround supermassive black holes. Okay? Fluid dynamics, and this is the really extreme of relativistic fluid dynamics, appears here. Here you have some simulations. The red part is the temperature, the purple part is the density, and here's just an image of what this plasma looks like from these simulations. So, how do we go to this? So what I'm going to start talking about the very tiny, the very small, microscopic, actually really microscopic collisions in the sense of collisions of nuclei and even protons themselves. And in order to talk about that, I have to give a very brief overview of the standard model, because in the end, the fundamental theory that governs those interactions is quantum chromodynamics. Afterwards, I'm going to make the transition to go from the very tiny to the very large. So we start with the standard model. So that's the standard cosmic pie chart. Here you have ordinary matter. So everything that we experience here is in this little 5% of the universe. The rest is dark matter and dark energy. And it got to a point that it can put in a nice little cup here. So there are fundamental forces in nature. Like there's a strong force. This is very relevant for the things that I'm going to consider here in this colloquium. There is the electromagnetic force, weak interactions, and also gravitation. And there are fundamental principles that dictate how these things interact and how you can construct sensible theories that describe these fundamental interactions. And they're rooted in relativity, like special relativity for these here, and also building that together with quantum mechanics. And symmetry is a very important underlying principle to construct such theories. So let me start with some basic facts about quantum chromodynamics. That's the fundamental theory that dictates what happens to quarks and gluons inside of the nucleus of the atom. So quantum chromodynamics is, from the technical perspective, we would say that this is a non-abelian gauge theory. What this means is that this theory has particles, and the particles the particles are the typical fermions. So they're kind of like fermions that you know, like electrons or positrons. But here you could have the fermions are called quarks. But also the interesting part is that the particles that mediate the interactions, they're called gluons. And different than the photons, the gluons actually can interact among themselves. So that's that appears just in this little, very simple diagram. We have 3 gluons interacting here. Here you have 4 gluon interactions. These are the gluon self-interactions. And the important part about this is that because you can have the gluons and the gluons interact like this, there is an important phenomenon called asymptotic freedom that says that interaction between these quarks and gluons change with the scale, and it changes in a very particular way, such that when the momentum exchange between these particles is very, very large, as you can see here, then the coupling is very small. And then when the momentum exchange, the typical scale is larger or smaller, then the coupling goes up. So this is a fundamental property of the standard model in QCD here. But one of the interesting phenomena that we see also has to do with the part that appears at strong coupling, where the coupling between these quarks and gluons is larger. This has to do with the physics of confinement that you see here. If you try to put together or separate out 2 quarks, like a quark and an antiquark here, in a meson, something like a pion. So originally, in the standard way, what happens if you try to separate them out, you put so much energy in the system that you actually create more and more of these mesons and these bound states with quarks. And this is just a nice picture showing how interesting the vacuum actually looks like. The vacuum is far from being just empty. There's a lot of quantum fluctuations going on. This is a very nice and old simulation, but I think illustrates the point that there's a lot of quantum jittering going on in these quantum field theories. So quark-gluon interactions provide a majority of visible mass. And in fact, they can explain the origin between the mass, the mass and the neutrons and the protons. And the part that I'm interested in here has to do when you put these quarks and gluons with temperature and density. So you try to do some like the statistical mechanics of these systems. So basically the point is the following. So normally these quarks and gluons are confined inside of the protons and the neutrons that are inside of the atoms. But one thing that is interesting that happens is that if you keep adding up the temperature, or if you try to squeeze them more and more, such that the density goes very large or the temperature goes very large, what happens when they reach a certain temperature that is basically the order of the pion mass, which is here in this unit is 150 MeV or 10 to the 12 Kelvin, then that's what I created here with this little dragon. So basically what happens is that when you had your standard nucleus with protons and neutrons, so the actual degrees of freedom of the system are not the standard neutrons and protons anymore. They actually become these quarks and gluons. And that's the type of physics that we're interested in. This has to do with the thing that we call the quark-gluon plasma. So how do you describe this? So if you are considering the system in equilibrium, and you consider the particular case where you have as many quarks as antiquarks, then it turns out that this system in equilibrium can be solved. And what I mean that it can be solved basically like using the standard properties that you do in statistical physics. So you write down some Lagrangian or some path integral here, but this case is just the partition function. This is just like you would do in a course, and you have, imagine you have some magnetic field, you have some spins, right? And you want to compute the partition function of this system. It just turns out that the system is a little bit more complicated. So you have your gauge fields, you have your fermions here, those are the quarks. And here, this is the action. This tells you how these things interact. So a lot of people worked on this, and especially here in this case in equilibrium, what you can do, instead of solving the system in the continuum, you solve this on the lattice, right? So there are well-defined prescriptions on how to transform this into this discrete version. And the overall message is that after many decades, this got to the point that is so well-defined that if you want to go around after this colloquium and just meet some random person on the street and say, oh, do you know what the pressure looks like for quarks and gluons when you have an equal number of quarks and antiquarks? If the person doesn't run away from you, the person would know that it turns out that this is basically a well-defined problem that we now know the solution. After many decades of collaboration between different groups, so this is just one representative simulation of this. So what you see is, so for the quark-gluon plasma, if you are in equilibrium, right, and you have the same number of quarks and antiquarks, you can actually plot the pressure of the system divided by the temperature to the fourth, and what you see as a function of the temperature. And what you see is a very interesting system. So here at very large temperatures, the system starts to behave like a gas of weakly interacting quarks and gluons because of asymptotic freedom. So this is what the case that I'm calling perturbative QCD. Here at low temperatures, the quarks and gluons, they combine, creating these bound states of QCD like mesons and baryons, like here. And then there's something in between that it's still deconfined in the sense that degrees of freedom should be quarks and gluons, but it's not really weakly coupled, or it's not really just described by these hadrons here. So this is the part that is actually pretty relevant for experiments. So in equilibrium, the overall message is that we understand what happens to these properties in this particular case. So we know what happens if you put quarks and gluons in a box. Now, what about out of equilibrium properties? So when, in any type of field theory, when you get the system out of equilibrium, things get much more complicated, and that's exactly what happens here. And there is some interesting historical thing. I was actually talking to Tom today. So there is some nice, some interesting paper by T.D. Lee that actually illustrates the idea of this, what we'll call here the heavy ion collisions. And it's basically the point. So, okay, to be clear, the actual paper nowadays is completely outdated and irrelevant. But the last sentence is pretty interesting. That's the last sentence. The last sentence says the following. In order to study the question of the vacuum, what happens to the, in this case here, as I'm interpreting the QCD vacuum, we have to do something different than particle physicists do. Particle physicists like to put a lot of energy into very small, space and time to, create very large mass things, right? Like the Higgs and things like that. For these experiments, it's different. The point is to still get a lot of energy, but you distributed this over in space and time. So the point is to see how energy flows in your system. So that's what this phrase is saying here. And the way that it's done now is that we try to understand what happens to this system, not at zero temperature, but at finite temperature. There are experiments. First, for example, you can see here at CERN, this is the LHC. And here is the, so this is an event display for one of those experiments. So basically, people measure a lot of particles. There are specialists here in this room that do this for a living. They can tell you much better than me how these things are measured. But the point is that this is under control after many decades that we try to understand the properties of this quark-gluon plasma formed in these reactions. So the overall picture is the following. Very qualitatively, what happens is this in these experiments. You accelerate these nuclei. They come at very, very large velocities, very close to the speed of light. That's what you see here. This is supposed to be like a Lorentz contraction effect, because the velocity is very close to the speed of light. So these are these two sheets are the nuclei. Lorentz contracted, okay? So they collide. They form something complicated, certainly not in equilibrium. And this system has quarks and gluons, and that's the thing that I'm going to call here eventually this QGP. So as time evolves, this system produces, so this is like, so in the beginning you had protons and neutrons, but afterwards what you did, you deposit so much energy that you disturbed the vacuum so much that quarks and gluons popped up out of the vacuum. So that's what you see here. This is what the quark-gluon plasma phase is. This system is produced, it has very, very large temperature, and as in any decent system that is expanding in vacuum, so as it expands, the temperature drops down. The interesting thing about this system is that it expands, and as I'm going to say later, to a very good approximation, this looks like a fluid. But note that it's a fluid under very, very small scales, because the typical size, if this guy is a very large nucleus, like lead or gold, the size is of the order of 10 Fermi. So this is 10 to the times 10 to the minus 15. And the temperatures are very large, and much larger, like 5 orders of magnitude larger than the largest temperature in the sun. And the time scales are very short. So the typical time scales that we're interested in, especially in the beginning, have to do like 1 Fermi over c. This is the time. This is the amount of time that it takes for light to go across a proton, more or less. So here you have this quark-gluon plasma phase that expands, and at some point, so it cools down. As it cools down, it starts to create these bound states again, this protons and pions. That's what is called here in this hadronic phase. And these things here still interact, and at some point, the system gets so diluted that it basically doesn't interact. It doesn't change the particle numbers anymore so much. It's still the case, of course, but then people measure this later. So that's what the experiment is showing here. So the overall consensus is that this quark-gluon plasma phase is very hot, very tiny amount of matter there. Can be described very nicely as relativistic viscous fluid. So it's relativistic because the velocities involved are really, really close to the speed of light. Okay? So it's viscous because I will see later, as it will show here later, there is indeed some, you can define things like shear viscosity or even bulk viscosity or particle diffusion for this system, just like you would do in a standard condensed matter or cold atom system. And so these equations can be derived in many different ways. So this is just to see a little simulation. That's what it looks like. So I have some energy density is expanding, and these little arrows just tell you what the flow velocity is going. So it's just something expanding in vacuum. And of course, this evolved significantly over the years. A state-of-the-art description requires doing many, many, many of these simulations to actually make comparisons to data. And the comparisons to data are actually very mature nowadays. So let me show you just one plot. So here, this is a very nice paper which appeared. So it was written by people here in the audience. That actually, what they show here is the following. This observable is the thing that I'm going to show here. When you do this model-to-data comparisons, what you do, you have the system expanding. This system cools down and produces these particles. These particles are produced, right? So what you do, you keep track of where or which particle got where and with what energy. Okay? So you can keep track of that and divide, basically do a Fourier analysis, and there are different modes. There is elliptic flow, triangular flow. But basically what this says, this counts the number of particles that go in a given direction and with what energy. That's what this energy here says here. This is called the transverse momentum. And here you see experimental data compared to hydrodynamic simulations. Okay? As you can see, there's a broad agreement, even for this particular system that I'm going to argue is pretty interesting. And this got to the point that people have books about it. Paul and Ulrika have this thing here that became a book that we use here in our field. So there's a lot of literature on this, and the simulations got really mature at this point. But there are still uncertainties, and that's what the rest of the seminar is going to be about. So one of the things that we found out that was not obvious from the outset, okay, is that this system behaves in a very weird way that I'm going to call here a nearly perfect fluid. And it appears in the following. This is a property that was not obvious at all from the Lagrangian of QCD. But basically, I'm talking about viscosity here, and precisely about the shear viscosity. The shear viscosity appears like this. So imagine I have some fluid. So this is a standard type of experiment. You have some fluid that is moving this way in the x direction, but it has a gradient in the y direction. Okay? So if you see this, you're going to find that there's going to be a force that appears on this upper plate. And the magnitude of this force has to do with a coefficient. This coefficient is called the shear viscosity. You can describe this using gases. So that's why I put here the little Boltzmann here. But here, what I'm actually considering is the ratio between this eta, the shear viscosity, this property related to dissipations, and the entropy. In this case here, the entropy density of the system. In natural units, this is dimensionless. And it turns out that if you do this for several systems, when you compare to what you would need from these model-to-data comparisons in the quark-gluon plasma, it turns out that this number is very small. Small enough that it's close to calculations coming from string theory, okay, in the context of the ADS-FT correspondence, so which is pretty exciting. But the overall point is that there is this new property of the system. The shear viscosity by the entropy ratio is very small, so small that creates some new effects. And this was certainly not obvious from if you just stare at the Lagrangian of QCD, you would not have known that that would be the case. So it's an emergent property of the system. Now, when it comes to hydrodynamics, I think this cartoon is really nice. So does this apply always, sometimes, or never? We certainly assume that this applies, but we got to the point, people have even written books about it. Now let's really try to understand if this is really a good description or not. And if it's a good description, what are the corrections, right? I mean, so this is something, if it's a good description, it should be improvable. We should, be able to consider corrections to this and see, some nice convergence. So let's try to make the argument why hydrodynamics should be a very good approximation to describe such systems. Well, over a decade or so ago, the idea was the following. So imagine that this is the energy density, right? So this is GeV per Fermi cubed. So it's just the amount of energy divided by the volume. And this, we just consider some transverse plane here. So this is X and this is Y. And this lump just tells you how much energy the thing has, okay? So you see that the energy is right here. There's more energy in here at the center than at the edges. If that's the case, then you would just start doing this sort of estimates, right? You say, okay, so let me try to estimate what the Knudsen number is. So I have to think about what is my macroscopic scale. So I'm just, seeing what are the gradients of conserved quantities, like energy, right? So if I divide how much the energy varies along the size of the nucleus here, that's what I define with this quantity here, 1 over L. And this L is, it could be just the size of the nucleus. That could be like 6, 7 Fermi. And if I divide this, or if I consider this together with the microscopic scale, don't even need to think about the mean free path. Just think about something like 1 over the temperature. Okay, in these units, 1 over temperature is a length scale. Okay, if you just divide these two and put it together, you'd find for this type of system that is very, very smooth, okay, you would think that this Knudsen number is not very small, but it's small enough. It's like 0.1, so that's probably a good approximation for a fluid. Okay, so that means that you have near equilibrium dynamics, a very nice state, in fluid dynamics at scales of the size of a large nucleus. However, it turns out the reality is much more complicated because, of course, nucleons like protons and neutrons, they are not little balls that collide, right? They are quantum mechanical objects. There are intrinsic quantum mechanical fluctuations already in the wave function of the nucleus as they collide, right? So for sure, that picture with everything was super smooth is not really realistic. It'll be probably something more like that, where you have peaks of energy density and valleys, and there's a lot of structure distributed across different scales. And if you try to do this, so I mean, the point is that there are unavoidable quantum fluctuations, and there could be, and in fact, we really expect that there are very large spatial gradients at very early times, right after the collision. This means that generically, the Knudsen number for these systems is not really small. Okay, so you start to worry whether hydrodynamics should be a good approximation. So in the end, theoretically, it's kind of like we have a paradox. The Knudsen number, which is the thing that motivated the hydro approximation in the very beginning, is not really small, but somehow hydrodynamics works. Works in the sense that you use these models and you compare to data and you get sensible results. So this issue must be understood. And as a theorist, I was already pretty excited about this, but of course experimentalists are much better. Not only they think about this, but they can go further and actually say, okay, so you're worried about separation of scales? Let me play a trick for you. Let me go there, instead of having a very large nucleus, let me make the system much smaller. In fact, let me make it as small as possible, even the collision of 2 protons, right? This is the smallest thing that you could consider here in the nuclear physics. And that's what people did. And the cool thing about this, though, is that, so here, these are not experimental data. These are just simulations showing you what happens if you collide not 2 gold nucleus, but proton with gold. So basically what happens, there is a size difference here. So the system is much smaller, and this is if you have deuteron or helium. This is just for the nuclear people. There's some nice spatial features that appear. And the cool thing about this is that actually there was a prediction. So people made the prediction using hydrodynamics for what this particle distribution should look like, and it looked very good afterwards. So after the experiments were out, they were able to see that indeed the predictions are broadly consistent. So what we see is that as you keep decreasing the system size, the fluid behavior seems to remain, even though this argument for separation of scales is not very solid. Why? What's going on here? Is it because maybe fluid dynamics is much more robust than we expected, and we just didn't understand the theory itself? So this goes under the name that I like to say, the surprising effectiveness of hydrodynamics in heavy ion collisions. And there are many outstanding questions in this field. For example, one of the perhaps the most fundamental one is how does hydrodynamics emerge from these very simple interactions that quarks and gluons can have as you define the Lagrangian of the theory, right? So of course, this is a complicated system. In general, you would not be able to do this even for simpler field theories, but it'll be interesting to know this for QCD, because in order to know this, if you can do that, you would be able to tell what is the viscosity of the quark-gluon plasma, right? And another question that I think is really important is how does this underlying non-abelian nature of QCD, the fact that the gluons interact here, really affect the emergence of hydrodynamics, okay? So these are questions that we are trying to understand nowadays, and this is just a cartoon to show you how complicated the system is. Imagine that you have a proton. Okay, so that's what this system here is a proton. This thing here is across like a 1 Fermi size. And okay, so now think about this. Remember everything that you studied before about fluid dynamics. And normally what you see for fluid dynamics, you say, oh, if I have a system, I can divide the system into a bunch of subsystems, and the subsystems interact. But in order for this to look like a fluid, you should still have enough particles in each one of these subsystems such that you can still do statistics and take averages and things like that. So let's try to play the game with the proton. If this is the proton, now, and what I say is that like this, let me cut this proton into a few pieces. Let me divide it into 10 pieces with the size of the order of 0.1 Fermi. Okay, so the whole thing is 1 Fermi, just dividing into 10. Just from the uncertainty principle alone, we would have large fluctuations in momentum in this system, okay? So this means that this thing, if it is a fluid, it does not look like a standard classical fluid that we expect. So somehow quantum fluctuations should matter in the actual description of hydrodynamics, and we still don't understand how that is the case for small systems. When you do the simulations for a small system, it seems that this is not there, and this is puzzling to me. So if you had to think about this in a big picture, okay? So if you think about the emergence of fluid dynamics in a bird's eye view, so I would write something like this. So this is the velocity involved. So here's daily life, like very, very small velocities in comparison to the speed of light. And quantumness is just like quantum effects, okay? So for us, for sure, quantum effects here are not really important to describe, how my hand is creating this fluid flow here. So we live right here. So this is this fluid. So you could either change the velocity going from non-relativistic to ultra-relativistic systems, for example, like in heavy ion collisions. So here, as you keep going to larger and larger velocities close to the speed of light, you could have these heavy ion collision systems that I described. But one cool thing that you can do there, as I said here, is that you can change the system size by colliding different types of nuclei, for example, from uranium to gold to even protons themselves. So you can decrease the system size, and the proton should really be a quantum object. So that's what I'm saying, that I'm going up in quantumness. So for example, if you put the velocity of, remove the velocity of light, just consider non-relativistic systems, if you go up here, you would find something like a Bose-Einstein condensate. So, and there are several other things that happen here that could have particles with spin and things like this. The other part that I'm very interested in, and I'm going to continue talking about during this colloquium, has to do not only with physics in this plane, which is what I was covering so far, but also the fact that you can create a new axis. And the new axis that happens is truly motivated by the observation of gravitational waves coming from neutron star mergers, is that you can also see what happens to fluid dynamics as you increase, for example, gravitational effects, and you start going towards neutron star mergers. So this is a nice way that we can actually connect the type of physics and formalism that we can develop here and apply it here, and vice versa. So today we are starting to see the beginning of the synergy between these fields, like gravitational fields, systems, very dense systems like neutron star mergers, and how the physics that you describe here in terms of fluid dynamics, how that can be useful to help you here, and vice versa. So what is the motivation here? So gravitational waves from neutron star mergers were measured in 2017. And really the point here is that you're probing ultra-dense matter, so matter that is even larger, so that has densities larger even than the density of the nucleus of an atom. And you can probe the properties of matter with gravitational waves. But one thing that is important to stress is that the properties of matter at extreme baryon densities, so imagine that the densities are very large, they're even larger than the densities of a nucleus of an atom. The properties of this type of matter remain unknown. And basically the point is this. So if this is the phase diagram, so every single point here is a point in equilibrium, and here I'm plotting the temperature and the baryon density. Okay, this tells you how many baryons are there in comparison to antibaryons. So this is baryons minus antibaryons. And of course, this is a cartoon. Okay, that's a very important point. So basically, the early universe and also these ultra-relativistic heavy ion collisions that I mentioned before, they're kind of here. Very large temperatures and very small net baryon density. Remember, I said in the beginning that we have basically equal number of protons and antiprotons, or quarks and antiquarks. So this regime is much more understood. Then there's going to be other experiments that are going to switch on in the next decade, trying to understand what happens when the temperature is not very small, but the density is much larger, approaching the densities of neutron stars. And there are several things that could happen. For example, you could have a line of first-order transitions. First-order transitions, just like you learned in statistical physics, that would end up in a critical point. We don't know if this critical point exists in the phase diagram of QCD. And there are so many different phases at very, very large, small temperatures and large densities. You have neutron stars, and you could have different phases of matter there. However, as I said, this is a cartoon. So if I had to put the part that we actually truly understand quantitatively, I would have to put something big on top to cover it. So that's what I'm saying here. There are very fundamental questions on how to compute this. And this is ultimately coming from the very fundamental problem that appears also in condensed matter related to the sign problem. When you try to do these type of calculations using fermionic systems like quarks, when you have a finite density, then there are fundamental problems that appear when you do your Monte Carlo sampling calculations. So we don't know what happens here, but this is very important for neutron stars. So for example, this is a Frankenstein of all the models that people use, okay? If this looks weird to you, and it doesn't look very systematic, that's the point. So you have the phase diagram of QCD, so you have the temperature here, the chemical potential, then lattice QCD covers some range at very small chemical potentials and large temperatures, and then there are several different people with several different models. And then there are some, Chiral-FT, which is a nice effective theory. So there are other models that are not really effective theory models, but there are several different ways to cover this more or less. And it's not very understood if the regime of applicability of one model overlaps with the other one, to the point that this is so serious and important for phenomenology when it comes to large density that one can get money for it to study this. So we are part of this collaboration called MUSES that is basically a collaboration to understand or to try to put together all these different models for the equation of state of neutron stars. So this is a collaboration with nuclear people, astrophysics, gravitational-wave scientists, and computer scientists with many institutions in different countries. But basically the idea is to create and put it together several different packages that people can use. And the idea is they're free and open source, and everybody can use in the community and make progress towards this field. So if you have interest in joining this collaboration, please talk to me. Now, the type of question I'm interested in here for the end of this colloquium is the following. What else can we learn besides equilibrium? Okay? Is there anything else that we can learn? Can we learn something about the out of equilibrium properties of this very large density matter that is from the neutron stars? So that's what this question is here. How does a lump of neutron-rich matter behaves under very strong gravitational fields? So this is a simulation by the Risola group. So basically they start with 2 neutron stars. So they collide. So this is the collision time here. So the scale is in milliseconds. As you can see, the system is rotating like that because, of course, the stars were spiraling towards each other. So they were rotating like this. And at some point, they collided. And the important thing to take care of, to pay attention here is the millisecond time scale. Okay? So this forms a very dense system that is rotating. So there's a lot of physics going on here. This is strong gravity, strong gravitational fields, and very strong, very large densities for this system. So besides the equation of state, what else can we learn? Okay? Of course, we can, and hopefully, we can learn or pinpoint some signatures of the emergence of deconfinement. right? So at some point, maybe the quarks are going to be the real degrees of freedom of the system. Maybe the densities are so large that we can actually see signatures of that. Maybe we can see some first transitions, some first order phase transitions appearing in this type of data. What I'm interested in here is about possible viscous effects. Okay, so can we use this type of simulations and this type of new window of the universe that opened up when we measure gravitational waves to actually learn what happens to this matter out of equilibrium? So when you start thinking about viscosity or dissipative effects, there are many dissipation sources. You could think about shear viscosity. That's the one I talked about before. You can think about thermal conductivity, right? So you have one plate here with this temperature, a temperature larger than this one, so you're going to see a gradient of temperature, right? So this is related to the thermal conductivity of the material. So all of these effects in principle are there. The one I'm going to focus here has to do with bulk viscosity. So bulk viscosity, if you don't study fluid dynamics, is not something that we see all the time. But bulk viscosity is basically the simplest way that you can dissipate. It's basically the simplest way that you can generate entropy in your system by basically doing the following case. Imagine that you have a system that can expand radially like this. As the system expands, so the energy will change, right? And the pressure will change. If there is a delay between how the energy changes and the pressure changes, this delay we normally call the bulk viscosity, okay? So that's what the bulk viscosity is, and this thing here is a bulk viscosity coefficient, zeta, okay? And people normally for gases like here, the air here, this is irrelevant, but there are different systems where bulk viscosity appears. For the QGP, it's something that people are trying to understand. But for the neutron stars, the way bulk viscosity appears, it's pretty interesting, very fundamental. Okay? It has to do with the physics of weak interactions. Basically, the point is the following. So imagine that what is happening, you have two neutron stars coming, they collide. As they collide, they bounce like this. And of course, you should have oscillations of the matter there. So the matter, the density, oscillates. So that's what you see here. You see some oscillations of the density as a function of time. Okay, so this is basically one element of the fluid. And you see how the element of fluid is varying its density, okay, as a function of time. If the system varies, the density should also vary the temperature, as you can see here. So there are very large temperature fluctuations as well in this system. But varying the density is really cool once you switch on the weak interactions. Because there are weak interaction processes that can actually be used to change the number of protons and neutrons in your system. So basically what happens imagine that you have a system full of neutrons, they have some oscillation, the density changes. As the density changes, the neutrons can go into a proton. This is called the RHIC process for the weak interaction. So the neutrons go into protons plus an electron and an antineutrino. And of course, you can also have protons getting an electron going to a neutron and a neutrino. You can also have other processes, higher order processes called modified RHIC process. So it's basically the same thing, but now you can pick up some nucleon in the system and have these interactions. And the way this works is such that, of course, as you change the density, you change the energy. As you change the energy, you change the pressure. If there is a delay, precisely because of these interactions, and if the time scales are precise in the correct range, such that this significant delay can be observed, this would lead to bulk viscosity, a delay between pressure and energy density. And this has been investigated by many people. And then it turns out that if you try to put some numbers, you get people that work on these numerical relativity simulations and see what the system looks like, then basically what you see here is an estimate for the size of this bulk viscosity here. And the system is still small, so the quantities are small, and this basically just tells you different densities with respect to the saturation density of the nucleus. But what the message you should get from here or from here is that, in principle, the processes are such that these viscous effects can happen, and there are several caveats coming up here. It depends on what happens to the neutrinos. Do the neutrinos get trapped? If the neutrinos get trapped inside of the system, if the mean free path of the neutrino is small enough that it can stay within this 10-kilometer radius of the neutron star, then these effects don't matter. But if you have regions where the temperature is low and there's some neutrino transparent regions where the neutrino, when it's produced, can just go away, this contributes to this dissipation part. That's what the bulk viscosity is showing up. And the amount of bulk viscosity in your system depends on how much you have for these neutrinos. So the overall message is that in principle, this could be there. There is some nice way to understand that. You can actually do some nice exact calculations showing that all these chemical reactions, number of protons changing into neutrons and stuff like that, can actually be described by bulk viscosity in an exact way. And this is valid even for large viscous stresses that would appear precisely when the neutron stars collide, which would be the worst kind of situation. So basically, the message is the following. For the simulations that people do nowadays, okay, so in these neutrino transparent regions, actually, these neutron star collisions are intrinsically bulk viscous systems. So if you were able to measure the effect of this bulk viscosity from the underlying gravitational wave emitted, you can actually get an idea of these viscous properties of neutron stars. And this is for the specialists in the audience. The equations of motion that come out to describe these systems are really the precise equations that we used before to describe these effects for the quark-gluon plasma, which is very exciting. So we see the synergy between these two systems.
I guess
yes?
The same, or I should say, how key is the signal?
Oh, it's very hard. But not hard enough that is pointless. So basically, there are several effects that come in. There are very big uncertainties from the equation of state, coming also how you put temperature in this simulation. So basically, the point is that the bulk viscosity uncertainty is as large as the uncertainty in the temperature. So if we had a better handle of the equation of state, we would be able to distinguish this.
But I guess maybe it's a simple question, like how would you tell apart like viscous?
Oh, yeah, so that's an important point. So far, the simulations don't actually include the shear. But in principle, it would be very hard to see because what you'd see generally is a damping and a change in the frequency of the gravitational waves. So it'll be very hard to tell if it's shear or bulk. But the thing that I didn't say here is if you try to estimate the effect from shear, it should actually be smaller than the one from bulk. So if we see something, probably is from bulk. That's the point. OK, so now that we start talking about neutron stars and strong gravity, so we have to start worrying about what happens to fluids in relativity, but also in general relativity. So what happens when you combine viscous fluid dynamics with general relativity? Of course, general relativity, it's just a very generic slide here, but it just basically tells you how geometry affects matter and matter affects geometry. So these are Einstein's equations. This is the energy momentum tensor of the matter. This tells you how energy and momentum is distributed in your system and how that changes the curvature of space-time, how space-time is curved because of the presence of energy and momentum. So it turns out, and it could be surprising to some of you if you don't work in this field, that it turns out that putting together viscosity or dissipation and relativity is actually not simple. You run into many, many different problems. And it is really that type of kind of problem for many decades. This is going back to Landon Lifshitz and Eckert in the 40s. And basically, the problem is the following. So if I can boil down to one simple slide, is that if you try to write down the standard generalizations of Navier-Stokes equations, so imagine that you get to your Navier-Stokes equations that worked for a classical non-relativistic system, and then you just try to make it such that it would work in relativity, you end up with weird problems. The first one, and a very serious one, is that you actually lose relativistic causality. Okay? So you break causality in these equations, and this actually leads to many different consequences. So one of the consequences that, in fact, the global equilibrium state, they state that, imagine that you have some fluid here, right? Any decent fluid, if you disturb it a little bit, it goes back to equilibrium, right? These systems, the way the equations are written, this would not be the case. Okay, so if you disturb a little bit, it would not go back to equilibrium, it would actually diverge exponentially, which was very, very strange. And the reason to understand that is actually very physical. It's basically the following. This is understood now that imagine that you have a system that violates causality. Imagine that you have something that the speed is larger than the speed of light. That's what I'm writing here, drawing here with this cone. This is a causal cone. So the speed of light is here. This is the light cone. Imagine that you have some disturbance, and then that's what you see here in this reference frame. And then you see the disturbance here is large in the beginning, but then it goes down. That's why the color here is stronger than here, okay? So the perturbation is stronger here than it is there. Now, if you boost, you consider another observer that is boosted here. So in the initial time, the observer would see this. That's what the initial time the observer sees. So in the beginning, you see some system here, but now as you see, because you boost it, if the system is acausal, if you can violate relativistic causality, what happens is that there are certainly Lorentz frames where if you evolve in time, you're going to see the opposite of dissipation. You see something very small in the beginning that keeps growing, growing, growing. That's what you see with the coloring here. It starts very weak and it goes larger and larger as it goes to other time frames here. So this is the onset of an instability. And all these other theories would have these issues. So I'm going to just mention a solution to this, which I'm involved. And it's basically the following. So this is, it's a little bit technical, but the point that you need to get here is the following. If you have a system in equilibrium, like this nice cup of coffee here, you can have some distribution of energy and momentum and some current of particles. That's what this J is saying. And in equilibrium, you can certainly attribute or create or define some temperature, some chemical potential, and some flow velocity for your system. Okay, so we have well-defined mapping here. However, if you go to equilibrium, your T mu nu, as you see here, it's not really, it's this in equilibrium. But if you go out of equilibrium, your energy momentum is still well-defined. I mean, these are just standard expectation values of operators in your quantum field theory. So this is still well-defined. But how you attribute what is temperature, chemical position, and flow, they are not uniquely defined. And what was realized recently is that there is a systematic way that you can take that into account. You can investigate every single possible way to define temperature and chemical potential and flow velocity out of equilibrium. And if you do that, that's what I'm saying here in very broad ways. And if you include and you do a systematic reasoning in terms of the smallness of this Knudsen number, so you say that the Knudsen number is small and you can do some expansion, it solves all of these problems. So you can get a nice generalization of Navier-Stokes equations. They're actually valid now in general relativity. You can prove several different things in mathematics. You can prove this is a causal system, it's stable, it's hyperbolic. So all the good things that you would expect to see in general relativity, this actually appears in this formulation. So this is really cool, and it can be used to do numerical calculations now. So for those that like theorems, those are well-defined theorems here. But basically, the message is, as you understand differently what is equilibrium and what happens in the system out of equilibrium, you can actually create a general relativistic theory of viscous fluid dynamics that can actually be used in all of these applications. So for conclusions here, so what I try to argue here is that heavy ion collisions provide a way to probe QCD out of equilibrium. Okay, so that's and this is the way for us to actually probe QCD under those conditions. And neutron star mergers will be crucial to unravel novel viscous phenomena that could appear in this ultra-dense, very high-density QCD matter that appears in these stars. I just briefly flashed this theory for you, so this is really for the specialists, that we have now a well-defined formalism that we can do calculations with, that have all the nice properties that we want, and people can use either in heavy ion collisions or actually even also in neutron star mergers. And I really believe that the synergy between heavy ions and neutron star mergers, I think it's really fruitful. And I really believe it's bound to lead to new fundamental questions about nature that we're only starting to ask now. Okay, thank you. Yes.
Hey, thanks again for the talk. It's kind of a silly question, but
Oh, that's a great question. It's actually not silly at all. It turns out the viscosity of these things. So I said that the effects, like for example, the QGP is a nearly perfect fluid because eta divided by S. S was the entropy density. So remember, the entropy takes care of the number of degrees of freedom. It turns out that the number of degrees of freedom is actually very large. If you just look at the viscosity itself, is fantastically large. much larger than anything that you can consider. In fact, for the bulk viscosity that I showed here for the neutron star mergers, okay? So there are several types of viscosity you can have. So for example, viscosity of air, viscosity of the tectonic plates here on Earth. The bulk viscosity of this thing is actually much larger than the one for those the crustal tectonic plates here on the Earth. So it's a fantastically large thing. But if you normalize by the correct quantity, which in this case is the entropy density, then the number is actually small. Yeah. No, if you divide by the density, it would still be of the same order, because the density and entropy are basically the same. They carry basically the same units here in this natural units. That's not for LIGO yet. Yes, that's a great point. That's a great point. That's why I didn't put the plot. Because I knew that my friend Jamie Nagel would come up with something like this. But the point is the following. So what LIGO actually measures is the in-spiral phase. So the neutron stars are very far away at first. They're like little dots. And then they start rotating towards each other, right? And at some point, so that's the in-spiral phase. So the in-spiral phase sort of ends when the distance between the neutron stars is comparable to their radius. That's when the standard post-Newtonian calculations are not really good, and then you have to start doing more numerical relativity calculations. So LIGO only sees the faraway stuff. Advanced LIGO and other things like the Cosmic Explorer thing should be able to see actually physics coming from the merger itself, but not yet. So these effects that I'm talking about, I concentrated on the effects coming from the merger. After the collide, they create this. But it turns out that it's actually pretty interesting, not in the very far in spiral phase, but as they get closer to each other, when the distance is comparable to the radius, then the stars start to get deformed. Then you actually start getting a little bit of these effects, but it's very small. It'll be great if it comes from the in-spiral. We're still trying to see if it comes from the spiral, but it could be complicated. Yes. Very good, very good. So in fact, that's a very good question, because for the two systems that I showed, so there will be this quark-gluon plasma first. In that case, the Reynolds number is actually not very large, because the system is so far from equilibrium in the beginning, where, so normally what we show, if I can use this, normally we plot something like this. So this thing here is like the bulk viscosity divided by the enthalpy of the system. This, in this language, will be the inverse Reynolds number, okay? And this number heavy ions of order 1 in the beginning. Afterwards, it gets smaller, but in the beginning, it was of order 1. So for example, if you're thinking about turbulence, maybe it's not there, at least from this, but it could be turbulence because, I don't know, maybe some jet goes through, creates a huge disturbance. This is something we can talk about later. But for the neutron stars, the neutron stars are interesting because there, this number is much smaller. So the Reynolds number associated is larger. And indeed, when people do these simulations with magnetohydrodynamics, they do see something that looks like turbulence. They do as realistic calculations as possible. Normally, they just do ideal hydrodynamics with electromagnetic fields. And they see things that look turbulent. But the actual number for turbulence to appear in this system, we know normally how turbulence appears in very controlled systems, like fluid in a pipe and stuff like that. As far as I can tell, the number should be larger than in heavy ions. The Reynolds number should be larger than in heavy ions. The people that do numerical simulations, they see evidence of something that looks turbulent because of the effects of the electromagnetic field. But I think I would end like that. Yes. Yeah. So in fact, there are so many issues because this thing is very expensive. Like so, In order to see turbulence, you need to get a very fine grid, and a very fine grid for this is extremely expensive in computational cost. So to the point that the people that claim to have seen turbulence, other friends of mine will say that you should not trust what they see because the simulation is not precise enough. But I think this will get there eventually. If you want to ask what relativist turbulence is, that'll be a nice question, and I'm thinking about that too.
Maybe then I have one other question about what you mentioned at the very end about the sort of, I guess, the sort of strictly causal theory or relativistic hydrodynamics. So, is this slide where you say it's sort of in the linear response?
Oh, I think it was why it's complicated here, or you mean here? Here, maybe.
Yeah. So I guess, so I think I would imagine that the normal sort of argument I would give here is to say, well, you know, if the speed of sound, let's say, is smaller than the speed of light, that only kind of some very weak, like viscous, might be a causal. Somehow this is like the cutoff